Hey guys, welcome back to Food for Thought Physics. In the last video, we looked at vectors in 2 dimensions, which we represented by arrows on the coordinate plane, and also learned how to resolve them into their x and y components, which are going to be how much the vectors point in the x direction and the y direction respectively. What we're going to do today is we're going to look at some of the various operations we can perform with vectors, starting with scalar multiplication, which, as its name might imply, is just going to be the multiplication of a vector quantity with a scalar quantity. Consider some vector on the coordinate plane. We're going to call this vector v. And one thing I forgot to mention last time, usually if we have some vector quantity, we're going to write it as v or some other letter with this little half arrow on top of it, or a vector hat as I sometimes call it. And what this vector hat tells us is just that this quantity is going to be a vector quantity and not a scalar quantity. In fact, usually if we write just a regular v without the hat, this is actually usually going to be the scalar magnitude of the vector v. We can also write this as the absolute value with the absolute value bars, but for simplicity we can just write it as v without the vector hat. And so we're going to assume that we've already resolved this vector into its 2 components. So I'm going to say that this v equals the ordered pair of v sub x comma v sub y. And now what we can do is we can multiply this vector v by some scalar, which I'll call n. So if we have some scalar quantity that's just a number, we can multiply it by this vector v, and the result is actually going to be another vector. We can get this new vector by just multiplying each individual component of the original vector by the scalar n. So for instance, n times the vector v is just going to be the x component of the new vector is n times v sub x, and the y component is, as you might expect, n times v sub y. Now let's look at what this means graphically. Well, if you remember, the angle theta formed between this vector and the x-axis is just going to be the inverse tangent of the y component over the x component. Here we see, well, we've multiplied both components by n, which means that their ratio is still the same, and that means that this angle here is not going to change. So this new vector is pointing in the same direction as the old vector. What's changed is the magnitude. We see that the x component is now going to be n times as far, and the y component is also n times as far. So you can sort of see that what this scalar multiplication does is it'll just make the entire vector either longer or shorter if n is less than 1 in the same direction. So for instance, if we had 2 times some vector v, that might be extending this vector by a factor of 2 in the same direction. Say like this. So for instance, this might be 2 times v. Alternatively, if we wanted to multiply this vector by, say, a half, that might end up with a new vector that's only half as long, but also in the same direction, say over here. So this could be, say, 1/2 v. So that's basically what scalar multiplication is. The formula here, as you can see, is kind of intuitive. It's not very difficult. And graphically, you can think of this as just either shortening or lengthening the vector in the same direction that it originally was at. So scalar multiplication is going to change the magnitude. It's actually going to multiply the magnitude by a factor of n, but it's not going to change the direction that the vector is in. The next operation we're going to look at is vector addition. Vector addition is going to be the addition of 2 vectors together to form another vector. To do that, first we need to add another vector to this diagram, which I'm going to put in blue. So let's say this new vector looks like this, and I'm just going to call this vector u, also with this hat on top of it to show that it's a vector. And we're going to resolve u into its components, which are going to be u sub x and u sub y. And so we can add these 2 vectors together, this v and u. To do this, we just add the components together individually. So for instance, we have v plus the vector u is going to equal the new x component is going to be v sub x plus u sub x, and the new y component is going to be v sub y plus u sub y. And we can visualize this graphically by using what we call the tail to tip method. So if you can imagine dragging this u upward, so that its tail over here, the tail of this vector, corresponds with the tip of this vector v, we can we can draw a new vector starting from here. It's going to be the same length as u in the same direction. Say looking something like that. Let's pretend this is correct. We have some vector u over here, and so we see that we've connected the tip of one vector to the tail of the other, or the tail of one to the tip of the other rather. That's why this is known as the tail to tip method. I'm going to write that here. The tail to tip method for addition. And this new vector, this v plus u, is actually going to be the vector that starts from the origin and goes to the new tip. So say from here all the way to here. This green vector here is going to represent u plus v, or v plus u. And we might notice, well, vector addition is going to be commutative. We can switch the order. So if we drag this v over here to where this u starts, and extend a v starting from the tip of u, then we get to the same spot. Which is also, and then we see, well, these two ways to add to the same spot. So vector addition is going to be commutative. And here we have this nice parallelogram. It doesn't look perfect because my arrows aren't perfect, but it should form a nice parallelogram. And this is why this tail to tip method is also known as the parallelogram method, because we can make this parallelogram, and the vector starting from one corner to the corner with the two tails, actually, all the way to the corner with the two tips is actually going to be this v plus u. Subtraction is kind of related, it's kind of similar actually. Subtraction you can think of as just adding the negative of this vector. So say if we wanted some v minus u, well, mathematically we could just subtract the components, which I don't have to write. But graphically, what we can imagine is we're adding some negative of u, and the negative of u we can think of as just the u, same magnitude, but in the opposite direction. So say this way, we could say, well, this vector here might equal negative u. And if we drag this to the tip of v, we can have something like that, maybe. Again, doesn't look perfect. We can just imagine that that's correct. And this yellow vector right here is going to be v minus u. So I'm going to write this down as v plus u, and over here, v minus u. What we can also do for the subtraction is think of it as a tip-to-tip method. We can take u, connect the tip of u to the tip of v, and the vector starting from the origin and ending at the new tail of u is going to be v minus u. So there are a few other operations we can do with vectors, such as the dot product and the cross product, namely, and they are ways to multiply two vectors together, and they are going to be used in other applications of physics. But for now, the main things we need to care about are vector addition and scalar multiplication, and so those other operations of vectors will be covered in future videos.